Welcome to the intersection of physics and history. We often wonder how we know the age of the ancient world. The answer lies in carbon-14 dating, how we date fossils. This isn't just a simple estimation tool. It is a revolutionary technique for dating organic remains that operates through the precise principles of nuclear decay. By understanding the atomic clock hidden inside living things, we can unlock the timeline of life on Earth. To understand the clock, we must first understand the gears, the atomic building blocks known as isotopes. Carbon is not a single uniform substance. It comes in three distinct varieties. First, there is carbon-12, which contains 6 neutrons and makes up 98.9% of all carbon. It is entirely stable. Then we have carbon-13, containing 7 neutrons, which accounts for just 1.1% and is also stable. Finally, there is the rare and vital carbon-14 with 8 neutrons. Unlike its siblings, it exists only in trace amounts and is radioactive. But where does this radioactive carbon originate? It begins high above us. Cosmic rays strike Earth's upper atmosphere in a continuous bombardment. This high-energy collision triggers a nuclear reaction that converts nitrogen-14 into carbon-14. It is a constant, natural process, creating the fuel for our biological clock. Once created in the sky, carbon-14 enters the biosphere. It starts with vegetation. Plants absorb carbon-14 directly from the atmosphere through the process of photosynthesis. From there, it moves up the food chain. Animals absorb this carbon-14 by consuming the plants or by eating other animals that have done so. In this way, every living thing is constantly replenishing its supply of radioactive carbon. The cycle of replenishment continues until one critical moment: death. When an organism dies, it stops exchanging carbon with the atmosphere. The intake ceases. At this precise moment, the unstable carbon-14 begins to decay, whilst the stable carbon-12 remains constant. This divergence sets the timer that scientists will read thousands of years later. What does this decay look like on an atomic level? It is a process called beta decay. Deep within the nucleus, a neutron in the carbon-14 atom decays into a proton and an electron. This electron is ejected as a beta particle, and the nucleus fundamentally transforms from carbon into nitrogen. It is a spontaneous transmutation that marks the passage of time. The utility of this science relies on the concept of half-life. For carbon-14, it takes exactly 5,730 years for half of the nuclei in any given sample to decay. This is a constant rate that remains completely unaffected by environmental factors like heat or pressure. This predictable decay is what enables the accurate dating of organic materials across millennia. We can visualize this process as the exponential decay curve. After one half-life, or 5,730 years, 50% of the original carbon-14 remains. Wait another cycle to 2 half-lives, or 11,460 years, and only 25% remains. By the time we reach 3 half-lives, which is 17,190 years, only 12.5% of the original radioactive isotope is left. So how do scientists determine the age? The measurement is based on ratio comparison. They measure the remaining carbon-14 to carbon-12 ratio within the sample. They then compare this to the constant ratio found in living organisms today. The difference between these two ratios reveals how long the organism has been dead. Modern dating requires incredible precision, provided by a technology called accelerator mass spectrometry, or AMS. This advanced method counts individual carbon-14 and carbon-12 atoms in a sample. Because it is so sensitive, it requires only tiny samples, which is crucial for minimizing damage to valuable artifacts. However, this tool has a horizon. There is a practical dating limit. The maximum dating range is approximately 50,000 years. Beyond this point, after about 10 half-lives, the remaining carbon-14 is simply too small to measure reliably. This serves as a significant limitation for dating older geological specimens that predate human history. Within that 50,000-year window, the applications for archaeology and history are immense. This science was essential for dating the Dead Sea Scrolls and the Shroud of Turin. It remains essential for dating human remains, textiles, charcoal, and wooden artifacts, allowing us to reconstruct the timeline of human civilization. There is a strict limitation: non-organic material. Carbon-14 dating cannot date inorganic materials such as rocks, minerals, or metals, because they were never alive to absorb carbon. For these materials, different methods are required, such as potassium-argon dating for rocks. The science assumes a global carbon-14 baseline. The method fundamentally assumes the atmospheric carbon-14 ratio is always constant. However, in reality, this ratio fluctuates due to phenomena like solar flares and human activity, meaning the starting line of the clock has shifted over time. To fix these fluctuations, scientists use calibration to correct the date. They use tree rings, a science known as dendrochronology, to establish a historical carbon-14 curve. Additionally, ice cores provide additional calibration data. This process converts the raw radiocarbon age into an accurate calendar date. Precision can be ruined by contamination sources. There is old carbon contamination, where contact with limestone makes samples appear older than they actually are. Conversely, modern carbon contamination, caused by handling or rootlets growing into the sample, creates the opposite effect, making samples appear younger. If we need to go back further than 50,000 years, we turn to dating older fossils using uranium-lead. Uranium-238 has a massive half-life of 4.5 billion years. While it cannot date the fossil itself, it is used to date rocks around the fossil layer. This provides an indirect maximum and minimum age estimation for the fossils trapped within. This leads us to the principle of stratigraphy. We know that upper layers are generally younger, while lower layers are older. The middle layers are the ones we target to be dated. In this context, carbon-14 dating provides the specific chronological context for the surrounding layers, anchoring the relative timeline with absolute dates. Recent history has left a permanent mark on this field: the impact of the atomic age. During the 1950s and 60s, atmospheric nuclear testing occurred. This generated a bomb pulse that released massive carbon-14 amounts into the atmosphere. While this temporarily skewed the natural baseline, it has proven useful for dating very recent organic materials. To summary, the nuclear clock is a cycle of nature. Carbon-14 is formed in the atmosphere from cosmic rays. It is absorbed by all life until death stops the process. From there, the remaining ratio determines age. It is a predictable exponential decay over 5,730 years that allows us to look back in time with confidence.